Hello, everyone. My name is Irvan from the University of Tokyo. I would like to make a presentation about our research titled Predicting Smartphone Users' Future Locations Through Deep Reinforcement Learning. Researchers have found that people are reasonably predictable in their travel movements. For example, they frequently visit certain locations from time to time. They also have favorite places that they would like to regularly visit that match their interest, their hobby, or other preferences. This predictability brings benefits for example, for web services and the users themselves. Location-based services can provide, for example, recommendation systems that recommend interesting places that users may enjoy. And the users will also benefit from this kinds of service where they can discover places that they would normally not discover by themselves. Predictability in movements can also potentially lead to better traffic management or a better evacuation system. For this research, we would like to find a machine learning model that can predict places that people are likely to visit in the future. A machine learning model that can learn based on those people's location history from past several weeks. And we would also like to apply that model on a relatively recent and, and a real world smartphone usage dataset. Existing research has also tried to tackle this problem to predict future locations. However, many of those research were conducted on an outdated dataset, for example, data that was collected before smartphone became ubiquitous. Other research also conducted their experiments based on training data that was gathered from dedicated devices, which means that the experiments was conducted under a controlled environment and the user's behaviors does not necessarily reflect their ordinary daily smartphone usage. And many of those research also conducted their experiments on a small number of participants. Researchers have found that deep neural network can be a reliable machine learning approach to predict location. In particular, a deep neural network that is trained with a reinforcement learning algorithms. Thus, for this research, we implemented a deep reinforcement learning model called DeepQ network, which in our implementation is a feed-forward deep neural network trained with a reinforcement learning method called deep learning. It is a method to train a deep neural network to interact with an environment and observe the reward outcome of its interaction. DeepQ network has been found to be useful in situations with many possible states. States that also happens in our case. It would normally take too long to compute every possible combinations of GPS coordinates. Our DQN model takes the following input to learn users' preferences. It takes input in form of user ID, day, time, and the GPS coordinates, the latitude and longitudes of their location during that particular day and time. The network that we implemented in this research consists of 5 fully connected hidden layers, where all hidden layers are made of 10 hidden nodes connected through a ReLU activation function. In this research, we used a GPS coordinates up to the third decimal places instead of pinpoint locations. It basically identifies neighborhood area of approximately 110 meters. This approach gives a general idea where users are more likely to be in certain areas instead of a certain pinpoint locations. Our model starts It's learning by feeding the DQN with the location data from the first week as training data, and then we task the DQN to predict locations that users will likely to visit during the following week at particular range of time. Over time, gradually, we increase the amount of training data by adding one more week and one more week again up until the 11th week. Predictions made are also consist of coordinates up to the third decimal places. Q-learning are used to inform about the quality of the predictions made by the DQN, by the model, by the neural network. So for this research, we use a dataset that is gathered through a collaboration between Social ICT Center at the University of Tokyo and several commercial companies which develop popular smartphone applications. So, and around 7,236 users of those smartphone applications agreed to participate. The GPS coordinates were collected from the user's own smartphone sensors, which reflects those users' actual day-to-day lifestyle. The project lasted for 3 months in year 2017. And the data is only used for research purpose and privacy is strictly protected. The image shows how gives you insights about how the data was stored inside the database. It collects the user ID, the date, the time, the latitude, and the longitude. Inside this dataset, not all users provide the same amount of data every week. Some users are less active in sharing location data than other users. So in this research, we conducted two experiments comparing two groups of users. One, we conducted an experiment that learned from the dataset from all the users inside the database. And the second experiment, we limit the learning only from the 100 most active users, which we define as users who share their location data most often. We also remove data considered as home and work locations based on the long period of stay at the same place because those places are easily deduced. And the information we also categorize the data into weekdays and weekends instead of each days. We also categorize the data into several time ranges according to the figure on the left: morning, noon, evening, and night. And data during midnight was not used because the users did not show many movements, presumably sleeping. And 3 predictions are made for each of these periods: weekday morning, weekday noon, weekday evening, weekday night, weekday morning, weekday noon, weekend noon, weekend evening, and weekend night. And we compare the predictions made by DQN with the list of actual locations visited by the users and calculated the accuracy of the predictions. So for our research shows that our experiment from this data set shows that data from the first couple of weeks are not enough to produce high accuracy in either case. Experiment with 100 most active users, for example, shows that after training the model up to the third week, DQN starts to generate accurate predictions more often. So in general, we found that 4 weeks amount of location history of data are enough to reach above 90% accuracy. On the other hand, when we conducted experiments with the DQN trained with the data from all users, on average, 8 weeks of location history of data are necessary for the model to start producing above 50% accuracy. However, we also found that the accuracy is actually still growing higher during the end of the data collection period. So we believe that even for less active users, higher accuracy would still probably be possible if they had participated longer. Another point of discussion is we would like to discuss about the growth of accuracy during the training. Figure on the right shows the average accuracy during various epochs while training for 100 most active users and with location data until the 11th week, which is actually the amount of data which produces the highest accuracy depicted in the previous figure. So this figure shows that early epochs are still far from achieving the best performance, but it might be enough for situations where computing time is an important factor, where real time real time prediction is very very important. So in this research, we conclude that active users experience high accuracy of predictions much more consistently. Crucial location based services such as evacuation systems benefit from these users the most. Meanwhile, entertainment location based services such as recommendation system may also benefit from less active users because their services are not as crucial. And our model is currently limited to produce accurate results with location history data containing at least 1 month of activities and does not predict locations on daily basis but rather in weekly basis. Addressing these limitations are our priority for future works. Findings from this research can be potentially implemented to bring look to bring more innovative location-based services, for example, and also to can also be implemented as a engine for behavioral authentications, which lead to a more sophisticated authentications. And that's all from me. Thank you for watching.